The signals are cut, the noise has faded. Welcome back to the Silence of the Black series. Today we walk together once more in the deepest corners of the universe, chasing the unknown. A new secret in every video, a moment of peace in every second. Don't forget to subscribe to stay with me on this journey. Take a deep breath. We are beginning. You float within the darkness of a cloud, a place where the boundaries between worlds blur and the ordinary becomes extraordinary. Around you, billions upon billions of water molecules drift in apparent chaos, invisible to the naked eye, moving randomly through the cool, saturated air. But something is about to happen here, something that happens billions of times every second across the planet. Order is about to emerge from chaos. The air within the cloud is supersaturated, holding more water vapor than it theoretically should. This is an unstable state, a temporary condition that cannot last. The water molecules, in their constant random motion, occasionally bump into something that gives them a reason to stop drifting and start gathering. It might be a tiny particle of dust, a speck of pollution, a fragment of sea salt carried thousands of miles by the wind. Whatever it is, it provides a surface, a nucleation point, a place to begin. When a water molecule encounters this surface, something remarkable happens. It does not simply bounce off and continue its random journey. It sticks. The molecule is held by weak electrical forces, hydrogen bonds that form between the slightly positive hydrogen of one molecule and the slightly negative oxygen of another. These bonds are individually fragile, easily broken by thermal motion, but together they have power. More molecules join the first, each one adding to the growing cluster. The hydrogen bonds form a network, a web of attractions that holds the molecules together. This is cohesion, the tendency of like molecules to stick to each other. It is the same force that allows water to form droplets on a leaf, that gives water its surface tension, that makes rain possible. You watch as the cluster grows, invisible at first, then becoming a tiny droplet barely larger than a few molecules across. It is not yet a raindrop, not even close. But it is a beginning, a seed from which something larger will grow. As more molecules join, the droplet begins to take on a shape. It is not a random shape, not an irregular blob. It is a sphere, or as close to a sphere as something this small can be. This is not an accident. It is a direct consequence of the forces at work. The water molecules on the surface of the droplet are pulled inward by the molecules below them, creating a force that compresses the droplet into the smallest possible surface area. For a given volume, the smallest possible surface area is a sphere. Mathematics demands it. Physics enforces it. The droplet becomes spherical because it has no other choice. This is surface tension, one of the most fundamental properties of liquids. It is the reason a carefully placed paper clip can float on water, the reason insects can walk on ponds, the reason water forms beads on a waxed car. It is a skin, an elastic membrane, a force field that holds the droplet together. But surface tension is more than just a physical property. It is a statement of resistance, a declaration that order can exist within chaos. The molecules inside the droplet are still moving, still vibrating, still full of thermal energy. But they are held, constrained, organized by the forces between them. The droplet is a tiny island of order in a vast ocean of randomness. You watch as the droplet continues to grow, adding more molecules, becoming larger and more substantial. It is now visible as a tiny speck, a point of light in the darkness of the cloud. It catches the faint illumination that filters through the cloud, scattering it, becoming visible. The droplet has achieved existence. The surface tension that holds it together is under constant assault. Other molecules crash into it, trying to join or to knock existing molecules loose. Thermal energy tries to pull it apart. The very act of growing creates stresses within the droplet that must be balanced by the cohesive forces. Yet the droplet persists, holds together, remains spherical. This persistence is remarkable. The forces holding the droplet together are weak individually, but collectively they are strong enough to resist the constant bombardment of the surrounding air. The droplet is a tiny fortress, its walls made of hydrogen bonds, its shape dictated by the mathematics of minimal surfaces. You think about the scale of what you are witnessing. This droplet, barely visible to the human eye, contains billions of water molecules. Each molecule is locked in a constant dance with its neighbors, forming and breaking hydrogen bonds millions of times per second. Yet the overall structure remains stable, the shape remains spherical, the droplet continues to exist. This is the birth of tension. This is the moment when cohesion creates order. This is the beginning of every raindrop that will ever fall. The droplet continues to grow, adding more molecules, becoming heavier. Eventually, it will become too heavy to remain suspended in the cloud. Gravity will pull it downward, and it will begin its long fall to earth. But for now, it floats, held aloft by updrafts and turbulence, waiting for the moment when it must leave. You look around and see that the droplet is not alone. The cloud is filled with millions of such droplets, each one a tiny sphere of water, each one held together by the same cohesive forces. They drift and collide, sometimes merging, sometimes bouncing apart. They are a community of droplets, a population of spheres, a forest of tiny worlds. The light that filters through the cloud catches them, scatters off their curved surfaces, creates halos and glories that you cannot see from inside but that are beautiful nonetheless. Each droplet is a tiny lens, bending light, creating rainbows that will only become visible when the droplets grow large enough to fall. This is the hidden world of the cloud, a world that exists above our heads every day but that we never see. It is a world of constant activity, of molecules joining and leaving, of droplets forming and growing, of forces balancing and shapes maintaining. It is a world governed by the silent physics of surface tension. The droplet you have been watching is now large enough to fall. Its weight exceeds the force of the updrafts that have been holding it aloft. It begins to descend, slowly at first, then faster as it grows and accelerates. It is leaving the cloud, leaving the community of droplets, beginning its journey to the ground. You watch it go, this tiny sphere born of chaos and held together by tension. It carries with it the memory of its formation, the history of its growth, the shape that physics demands. It is a raindrop now, a true raindrop ready to complete its journey. The birth of tension is complete. The droplet has been born. The rain has begun. The droplet falls. It has left the protective embrace of the cloud, the community of millions of other droplets that surrounded it during its formation. Now it is alone, a tiny sphere of water plunging through a vast expanse of air. The journey ahead is measured in thousands of feet, a tremendous distance for something so small. And every inch of that journey is a battle. The moment the droplet leaves the cloud, it enters a new world. The air here is different, drier, warmer, moving in complex patterns that the droplet cannot see but can certainly feel. This air is not empty. It is filled with molecules of nitrogen and oxygen, with particles of dust and pollution, with the constant random motion that defines the gaseous state. And every one of these molecules that the droplet encounters is a potential threat. The droplet begins to accelerate. Gravity pulls it downward with a force proportional to its mass. At first, the air offers little resistance, and the droplet falls faster and faster. But as its speed increases, something changes. The air molecules it encounters are no longer gentle nudges. They are impacts, collisions, forces that push against the droplet's forward motion. This is drag, the resistance of the air to anything moving through it. For a falling raindrop, drag is the enemy of speed, the force that limits how fast it can fall. But drag is more than just a brake. It is a deformative force, a pressure that pushes against the droplet's leading surface, trying to flatten it, distort it, destroy its perfect spherical shape. You zoom in closer and closer, until you can see the individual air molecules as they approach the droplet. They are tiny compared to the droplet itself, but there are so many of them, billions upon billions, each one carrying momentum that will be transferred to the droplet upon impact. The droplet's leading edge, the part facing downward as it falls, is under constant bombardment. The force of this bombardment is not uniform. The center of the droplet's leading edge receives the full force of the onrushing air, while the sides receive less. This creates a pressure differential, higher in the center, lower toward the edges. And pressure differentials in the world of fluids mean one thing: deformation. The droplet wants to remain spherical. Surface tension, the same force that shaped it in the cloud, pulls inward equally in all directions, trying to maintain that minimal surface configuration. But the pressure of the air pushing against its bottom is not equal in all directions. It is concentrated, focused, intense. The droplet's bottom begins to flatten, just slightly at first, a barely perceptible deviation from perfect sphericity. This is the microscopic struggle. On one side, surface tension, the cohesive force that binds water molecules together, that creates an elastic skin, that demands spherical perfection. On the other side, aerodynamic pressure, the force of the air resisting the droplet's passage, pushing, pressing, demanding deformation. The droplet is caught between these two forces, and its shape is the battlefield. You watch as the battle intensifies. The droplet falls faster and the pressure on its leading edge increases. The flattening becomes more pronounced, the deviation from spherical more obvious. The droplet is no longer a perfect sphere. It is becoming something else, something distorted by the very act of falling. But surface tension does not give up easily. The molecules on the droplet's surface feel the distortion and respond. They pull more strongly in some directions, less in others, trying to restore the spherical shape. It is as if the droplet has a memory of its ideal form and is fighting to return to it. This is not a metaphor, it is physics. The surface tension of water is about 72 millinewtons per meter at room temperature, a specific, measurable quantity. The pressure on the droplet's leading edge can be calculated from its speed and the density of the air. The battle between these forces can be modeled, predicted, understood. And at this stage of the droplet's fall, they are nearly balanced. The droplet reaches a critical speed, the point at which the force of gravity pulling it down equals the drag force resisting its motion. This is terminal velocity, the maximum speed the droplet can achieve. For a small raindrop, this might be about 2 meters per second. For a large one, up to 9 meters per second. At this speed, the forces are in equilibrium, and the droplet falls steadily, no longer accelerating. But equilibrium does not mean the battle is over. The pressure on the droplet's leading edge continues, constant now, unrelenting. The droplet's shape is no longer changing, but it is not spherical either. It has reached a compromise, a shape that balances the inward pull of surface tension with the outward push of aerodynamic pressure. This shape is not what you might expect. It is not a sphere, not a teardrop, not anything that popular culture has taught you to imagine. It is, in fact, something closer to a hamburger bun, rounded on top, flattened on the bottom, with a slight indentation where the pressure is highest. This is the shape of a falling raindrop, the result of the microscopic struggle between cohesion and collision. You watch as the droplet falls, its shape a testament to the forces acting upon it. The top remains beautifully curved, almost spherical, where surface tension has free rein. The bottom is flattened, distorted, pressed inward by the constant assault of air molecules. The sides bulge slightly, pushed outward by the internal pressure created by the flattening. It is a complex shape, a dynamic shape, a shape that could only exist in the context of falling. The droplet is not alone in its struggle. All around it, millions of other droplets are falling too, each one engaged in the same battle. Some are smaller, their surface tension strong enough to maintain near-perfect sphericity despite the pressure. Some are larger, their greater mass making them fall faster, subjecting them to greater pressure and more extreme deformation. Each droplet's shape tells the story of its size, its speed, its journey. The air through which they fall is not uniform. It moves in currents, rises and falls in temperature, changes density with altitude. Each change in the air affects the battle. A sudden updraft can slow the droplet, reducing the pressure and allowing surface tension to restore some sphericity. A downdraft can accelerate it, increasing the pressure and causing further deformation. The droplet's shape is constantly responding, constantly adapting, constantly fighting. You think about the energy involved in this struggle. The droplet gains kinetic energy as it falls, energy that comes from the gravitational field of the Earth. Some of that energy is dissipated as heat, generated by the friction of air molecules sliding past the droplet's surface. Some is stored as potential energy in the deformed shape, energy that would be released if the droplet could suddenly relax back to spherical. The droplet is a system in motion, constantly exchanging energy with its surroundings. The battle is not just about shape. It is also about survival. The same forces that deform the droplet can, under the right conditions, destroy it. If the pressure becomes too great, if the deformation becomes too extreme, the droplet can break apart, splitting into smaller droplets that then begin their own struggles. This is how rain becomes mist, how showers become drizzles, how the size distribution of raindrops is determined. You watch as a nearby droplet larger than yours reaches this breaking point. Its bottom has become so flattened, so indented, that the surface tension can no longer hold it together. The indentation deepens, becomes a cavity, then a hole. The droplet stretches, thins, and finally separates into two smaller droplets, each one now beginning its own fall, its own struggle. This is the fate of many raindrops. They do not reach the ground as the same droplets that left the cloud. They break, merge, change, transform. The rain that falls on your head is not the rain that left the cloud. It is the product of countless battles, countless struggles, countless microscopic wars. Your droplet continues its fall, stable for now, its shape a dynamic equilibrium between the forces that would destroy it and the forces that hold it together. It has reached a kind of peace, a truce in the microscopic struggle. The battle continues, but it is at a stalemate. You follow the droplet as it falls, watching the constant play of forces on its surface. The air molecules continue their bombardment, billions upon billions per second. The surface tension continues its pull, holding the molecules together against the assault. The droplet remains intact, remains falling, remains alive. The ground is still far below, but the droplet is getting closer with every second. The air is becoming denser, warmer, more turbulent. The battle is about to enter a new phase, as new forces come into play and new challenges arise. But for now, the droplet falls, a tiny warrior in a microscopic struggle, a perfect example of the silent physics that governs every raindrop that has ever fallen. You float alongside the falling droplet, witnessing the microscopic struggle between surface tension and aerodynamic pressure. But now, something remarkable is happening. The droplet has reached a moment of perfect balance, a fleeting instant when the opposing forces cancel each other exactly. In this moment, the droplet becomes something extraordinary, a shimmering, near-perfect sphere that catches the light like a tiny crystal falling through the air. This moment does not last long. It cannot last long. The forces at play are too dynamic, too constantly changing. But for a brief period, measured in fractions of a second, the droplet achieves a kind of perfection that is rarely seen in nature. It is a sphere, almost mathematically exact, its surface curved with a precision that would be the envy of any glassmaker. To understand how this happens, you must understand the relationship between the droplet's size, its speed, and the forces acting upon it. Small droplets, those less than about 1 millimeter in diameter, are dominated by surface tension. The cohesive forces holding them together are strong relative to their mass, and they remain nearly spherical throughout their fall. These droplets are the ones that form mist and drizzle, falling slowly, their shapes undisturbed by the rush of air. Large droplets, those greater than about 4 millimeters in diameter, are dominated by aerodynamic forces. Their greater mass makes them fall faster, subjecting them to higher pressures that deform them significantly. These are the droplets that become flattened, distorted, that may even break apart as they fall. They are the ones that create the heaviest rain, the droplets that splatter when they hit the ground. But your droplet is in between. It is just the right size, about 2 millimeters across, to experience a temporary equilibrium. It has fallen far enough to reach terminal velocity but is not so large that the aerodynamic forces overwhelm surface tension. In this narrow window of size and speed, the droplet can achieve a moment of perfect balance. You watch as the droplet's shape shifts, responding to the constantly varying pressure of the air. The bottom, which was flattened by the onrushing molecules, begins to recover. The surface tension pulls it back, restoring curvature. The top, which remained rounded, stays as it was. For an instant, the droplet is a perfect sphere. In that instant, the light changes. Sunlight, passing near the droplet, does something remarkable. It bends, it splits, it dances. The droplet acts as a lens, focusing light from behind it, creating patterns of brightness and color that shift and change as the droplet rotates. For a moment, the droplet glows as if lit from within, a tiny star falling through the air. This is not magic, it is optics. A spherical droplet of water has a refractive index of about 1.33, meaning it bends light more than air does. When sunlight strikes the droplet, it is refracted twice, once entering, once leaving, and reflected off the back surface. This combination of refraction and reflection creates the familiar rainbow, but even in a single droplet, the effect is beautiful. You see the colors separate as the light passes through the droplet. Red at 42 degrees bends the least. Violet at 40 degrees bends the most. In between, the entire spectrum unfolds, each color taking a slightly different path through the droplet. For a moment, the droplet becomes a prism, splitting white sunlight into its component colors. The droplet rotates slowly as it falls, caught by subtle variations in the air. The colors shift and change, moving across its surface like oil on water. One moment it appears red, the next blue, the next green. It is a chameleon, a shapeshifter, a tiny display of chromatic beauty. You think about the conditions necessary for this moment. The droplet must be the right size, falling at the right speed, illuminated from the right angle. The air must be clear enough for the light to reach it, calm enough for the droplet to maintain its balance. So many factors must align perfectly for this shimmer to occur. And yet, it happens billions of times every day. Every rainstorm contains countless such moments, each droplet experiencing its own brief instant of perfection. Most go unseen, falling in darkness or in clouds, their beauty hidden from human eyes. But occasionally, when the sun breaks through the clouds just as the rain is falling, we are granted a glimpse of this hidden world. The rainbow that appears in such moments is not a thing in itself. It is an illusion, a trick of light, a collective effect of millions of droplets, each doing what your droplet is doing now. Each droplet sends its own colored light toward your eyes, and your brain combines them into the familiar arc. The rainbow is a synthesis, a construction, a product of your perception. But the droplet shimmer is real. The light really does split. The colors really do separate. The droplet really does become, for an instant, a tiny crystal falling through the air. You watch as the moment passes. The droplet's shape begins to change again, the perfect sphere giving way to the inevitable deformation of continued fall. The colors fade, the glow dims, the droplet returns to its ordinary state. The shimmer is over, but the memory of it remains, etched into the droplet's brief history. It has known perfection even if only for an instant. It has been beautiful even if no one saw it. It has done what droplets do, what they have always done, what they will always do. The droplet continues its fall, but you stay with the moment a little longer. You think about the nature of perfection, about how it exists only in fleeting instants, about how we spend our lives chasing moments that are inherently temporary. The droplet does not chase, it simply falls. Perfection finds it or does not, and it continues either way. This is the lesson of the shimmering spheres, that beauty is temporary, that perfection is fleeting, that the most glorious moments are often the briefest. The droplet does not mourn the loss of its perfect shape. It simply continues its journey, accepting each moment as it comes. You watch as other droplets around you experience their own moments of perfection. Each one, at its own time, in its own way, becomes a shimmering sphere. The air is filled with these tiny flashes of beauty, these brief instants of perfection, these falling stars of water. The sun, low in the sky, casts long shadows through the rain. The droplets catch its light, each one becoming a tiny point of brilliance. The effect is overwhelming, a cascade of shimmering spheres falling from the sky, each one unique, each one beautiful, each one gone in an instant. You reach out your hand and let a droplet land on your palm. For an instant, it remains spherical, a tiny bead of water resting on your skin. You see the light bend around it, see the colors separate, see the shimmer that you have been watching from afar. Then it flattens, spreads, becomes part of the thin film of water on your hand. The moment passes, but you have seen it. You have witnessed the shimmering sphere in its moment of perfection. You have held it, if only briefly. You have been part of its journey. The droplet is gone now, merged with the water on your hand, but its memory remains. It joins the countless other droplets that have landed on countless other hands throughout history, each one a tiny ambassador from the sky, each one carrying the story of its formation, its struggle, its moment of perfection. You look up at the falling rain, at the millions of droplets still descending, and you know that each one is having its own moments, its own struggles, its own shimmering instants. The rain is not just water falling. It is a symphony of individual journeys, each droplet a soloist in the great chorus of the storm. The shimmering spheres continue to fall around you, each one catching the light in its own way. The air is alive with their brilliance, a display of natural beauty that rivals any human creation. And you stand at the center of it, a witness to the silent physics that makes it all possible. This is the moment of the shimmering spheres. This is the brief perfection of the falling droplet. This is the beauty that exists in the space between formation and destruction. The moment of perfection has passed. The shimmering sphere, that brief instant of ideal form, is gone. What remains is a droplet under duress, a tiny world being pressed and shaped by forces it cannot control. The balance has shifted and gravity is demanding its due. You watch as the droplet continues its fall, its speed increasing as it drops through layers of increasingly dense air. The terminal velocity that once held it in equilibrium is now a memory. The droplet is accelerating, responding to the ever-present pull of Earth's gravity. With each increase in speed, the pressure on its leading edge grows stronger. The shape that was once a perfect sphere begins to change visibly. The bottom, already flattened, becomes more so. The indentation that was barely perceptible deepens, creating a concave surface where the air pressure is most intense. The sides bulge outward, pushed by the internal pressure created by the flattening. The droplet is becoming something new, something strange, something that bears no resemblance to the idealized teardrop of popular imagination. This new shape has a name, though it is not a scientific one. Meteorologists and physicists call it the hamburger bun shape, and for good reason. The droplet is rounded on top, flat on the bottom, with a slight depression in the center of that flat surface. It looks exactly like a bun waiting for a patty, a shape that would be comical if it were not so serious. The physics behind this shape is elegant in its complexity. The air pressure on the droplet's leading edge is not uniform. It is highest at the center, where the airflow is directly opposed, and lower toward the edges, where the air can flow around more easily. This pressure distribution creates a force that pushes the center of the droplet's bottom upward, creating the indentation. At the same time, the surface tension that once held the droplet in a perfect sphere is still at work. It pulls inward everywhere, trying to minimize the surface area. But the pressure from below is stronger, and the droplet must respond. The sides bulge outward because that is where the surface area can increase without fighting the pressure directly. The droplet is a study in compromise, a physical negotiation between opposing forces. It cannot be spherical because the pressure will not allow it. It cannot be completely flat because surface tension will not allow that either. So it becomes this strange hybrid, this flattened form that is neither sphere nor disk but something in between. You watch as the indentation deepens further. The droplet is now falling at nearly 9 meters per second, its maximum possible speed for its size. The pressure on its bottom is immense, at least from the droplet's perspective. The center of the flat surface is now distinctly concave, a tiny bowl-shaped depression that catches the air and holds it. This is the moment of maximum stress. The droplet's surface tension is stretched to its limit, holding together against a force that would tear it apart. The molecules on the bottom are pulled in two directions: inward by their neighbors trying to maintain cohesion, and outward by the pressure of the air trying to separate them. It is a microscopic tug of war, and the outcome is uncertain. You wonder how much more the droplet can take. The pressure is not going to decrease. If anything, it will increase as the droplet falls into denser air. The surface tension is fixed, a constant property of the water itself. Something has to give. For most droplets, something does give. They reach a critical size, a critical speed, a critical pressure, and they break. The indentation deepens until it becomes a hole, and the droplet splits into two or more smaller droplets. These smaller droplets then begin their own falls, their own struggles, their own journeys. The cycle continues. But your droplet is resilient. It is large enough to experience significant deformation but small enough to resist breaking. The indentation reaches a maximum depth and then stabilizes. The droplet has found a new equilibrium, a shape that balances the forces as well as possible. It is not beautiful, not in the way of the shimmering sphere, but it is stable. This stability comes at a cost. The droplet's internal pressure is now higher than it was when it was spherical. The molecules are pushed closer together, their bonds stretched and strained. The droplet is under tension in a very literal sense, its very substance stressed by the demands of its fall. You think about what this means for the droplet's journey. It will continue to fall, maintaining this flattened shape, until it reaches the ground or until something changes. A shift in the wind, a collision with another droplet, a change in air density, any of these could upset the delicate balance and send the droplet back into a state of flux. The droplet is not alone in its deformation. All around you, millions of other droplets are experiencing the same pressures, the same flattening, the same struggle. The rain is a cascade of flattened forms, each one a tiny testimony to the power of aerodynamic force. You notice that droplets of different sizes have different shapes. The smallest ones, less than a millimeter across, remain nearly spherical. Their surface tension is strong enough to resist the pressure almost completely. They fall slowly, gently, their shapes undisturbed by the rush of air. The largest ones, those approaching 5 millimeters, are the most deformed. Their bottoms are deeply indented, their sides bulging dramatically. Some have already developed the characteristic dimple that precedes breakup. They are living on borrowed time, their existence as single droplets soon to end. Your droplet at 2 millimeters is in the middle. It is deformed but stable, flattened but intact. It represents the majority of raindrops, the ones that will reach the ground as themselves, that will complete their journey without breaking apart. The ground is closer now, much closer. You can see it through the rain, a dark surface waiting to receive the falling water. The droplet's journey is almost over. Soon it will encounter that surface and its shape will change one last time. But for now, it falls, flattened by demand, shaped by pressure, a tiny world in free fall. The forces that act upon it are the same forces that act upon everything that moves through air: drag, pressure, resistance. The droplet is a demonstration of these forces, a visible example of physics in action. You think about the word demand in the context of this fall. It is an anthropomorphism, of course. Gravity does not demand, air does not demand. They simply are, and their being creates conditions that the droplet must meet. The droplet's shape is not a response to a demand but an inevitable consequence of physical law. And yet the word feels right. There is something imperative about the way the droplet's bottom flattens, something inexorable about the progression from sphere to disk. The droplet is being asked to change, and it has no choice but to comply. The rain continues to fall around you, each droplet responding to the same demand in its own way. Some flatten more, some less. Some break, some hold together. Some will reach the ground, some will evaporate before they get there. Each one's fate is written in its size, its speed, its journey. Your droplet falls on, its flattened form a testament to the power of the air through which it moves. The ground rushes up to meet it, and you know that its journey is almost over. One final transformation awaits, one final change of shape before it becomes part of something larger. The flattened demand has been met. The droplet has responded to the pressure, has taken the shape that physics requires. It has done what droplets do, has fallen as droplets fall, has been what droplets are. The ground is seconds away now. The droplet's long fall is about to end. But even in these final moments, the forces continue to act. The shape continues to adjust. The silent physics continues its work. You watch as the droplet prepares for its final encounter, its shape still flattened, its surface still stressed, its journey almost complete. The ground approaches. After a journey that began high in the clouds, after moments of perfect spherical beauty and long stretches of flattened deformation, after countless collisions with air molecules and near misses with other droplets, your raindrop is finally about to complete its descent. The end is near, but the physics is not done. One final transformation awaits. You watch as the droplet falls through the last few meters of air. The ground below is a complex landscape: soil particles, blades of grass, tiny crevices and valleys that exist at a scale the droplet can understand. Each feature will influence what happens in the next few seconds, shaping the droplet's final moments in ways that are both chaotic and predictable. The droplet is still moving at terminal velocity, about 9 meters per second for its size. At this speed, the impact with the ground will be significant. The forces involved are immense from the droplet's perspective, far greater than anything it has experienced during its fall. The surface tension that has held it together throughout its journey is about to face its ultimate test. But before the impact, something else happens. In the last millimeter above the surface, the droplet encounters a boundary layer of air that is moving differently from the air above. This layer, only a few molecules thick, is influenced by the ground itself, creating a cushion that the droplet must push through before it can reach the surface. This layer slows the droplet slightly, reduces its speed, softens the impact that is about to occur. You slow time down, stretching these final milliseconds into something you can observe. The droplet's bottom, already flattened by aerodynamic pressure, begins to change again. As it approaches the surface, the air between the droplet and the ground is compressed, creating a high-pressure region that pushes back against the droplet. The indentation that formed during free fall deepens dramatically, becoming a concave cavity that traps a small pocket of air. This is the moment of first contact, not with the ground itself, but with the air that is about to be compressed between droplet and surface. The droplet's shape is now more distorted than at any point in its journey. The bottom has become a deep bowl, the sides flared outward, the top still rounded. It looks nothing like a sphere now, nothing like the perfect form it briefly achieved. It is a shape born of pressure and proximity, a shape that exists only in the final instant before impact. Then the droplet touches the ground. The contact is not a single event but a cascade of events unfolding in microseconds. The center of the droplet's bottom hits first, touching a tiny grain of soil. Immediately, the water begins to spread outward, rushing away from the point of impact at speeds far greater than the droplet was falling. The droplet is not splashing in the dramatic sense. It is too small for that, but it is spreading, flowing, becoming something new. The spreading is driven by the droplet's momentum. The water that was falling downward now has nowhere to go but sideways, and it takes that path with incredible speed. A thin film of water shoots outward from the impact point, covering the soil, filling tiny crevices, wetting individual grains. In the first millisecond after impact, the droplet has already transformed from a discrete sphere into a thin, spreading disk. But the story does not end there. The surface tension that has been the droplet's constant companion throughout its fall now reasserts itself in a new way. The thin film of water spread across the soil is unstable. It wants to beat up, to form droplets again, to return to the spherical form that minimizes surface area. On a perfectly smooth, non-absorbent surface, it might do just that, forming a cluster of tiny beads that sit on the surface like morning dew. But the soil is not smooth. It is rough, porous, absorbent. As the water spreads, it encounters countless tiny spaces, pores between soil particles, cracks in organic matter, the intricate architecture of the ground. Capillary action, the same force that allows water to rise in a thin tube, now pulls the water into these spaces. The water is absorbed, drawn downward into the soil, becoming part of something larger than itself. You watch as the droplet disappears. In less than a second, the discrete entity that fell so far, that struggled so valiantly against the forces of air, that briefly achieved perfect spherical beauty, is gone. Its water molecules have joined the soil, becoming part of the complex matrix that supports plant life, that hosts countless microorganisms, that forms the foundation of terrestrial ecosystems. But the droplet's journey is not truly over. The water that was once a droplet will continue to move, drawn by gravity deeper into the soil, pulled by roots into plants, evaporated by the sun back into the atmosphere where it will form new clouds and new droplets. The cycle continues. The droplet's molecules will make this journey countless times over the eons, each time taking new forms, new shapes, new roles in the great water cycle. You pull back away from the wei quan shi jie and look at the broader scene. All around you, millions of droplets are completing their own journeys, each one impacting the ground in its own way. The sound of rain is the collective voice of these countless impacts, a symphony of tiny events that together create the soothing rhythm of a storm. Each impact is unique. Droplets that fall on bare soil create different patterns than those that fall on leaves. Droplets that fall on water create different effects than those that fall on stone. The size of the droplet, the speed of its fall, the nature of the surface it strikes. All these factors combine to create an infinite variety of final moments. You listen to the rain and hear, in its patter, the stories of billions of droplets. The high-pitched ticks are the smallest droplets, their impacts barely perceptible individually but collectively creating the background whisper of the storm. The deeper taps are the larger droplets, their greater mass producing more substantial sounds. The occasional splat is a very large droplet, one that maybe broke apart on impact, its water scattering in multiple directions. The sound is not random. It has structure, rhythm, pattern. The spacing between impacts, the distribution of sizes, the way the sound changes as the storm intensifies or weakens. All of these are governed by the same physical principles that shaped each droplet's fall. The rain is speaking, and if you listen carefully, you can hear the physics in its voice. You think about the restorative nature of this descent. The droplet that began as vapor in the cloud, that condensed around a tiny particle, that grew and fell and struggled and flattened, has now returned to the earth. In doing so, it has brought water to the soil, water that will nourish plants, support life, sustain ecosystems. The droplet's journey was not just a physical process. It was an act of restoration, a returning of water to the places where it is needed most. The rain has this effect everywhere it falls. It quenches the thirst of parched earth, fills rivers and lakes, recharges underground aquifers. It washes dust from leaves, cleans the air of pollutants, brings life to barren landscapes. The restorative power of rain is one of the most fundamental cycles on Earth, a process that has been operating for billions of years. Your droplet, in its small way, has contributed to this cycle. Its water molecules will now participate in the complex dance of life, taken up by roots, transported through stems, used in photosynthesis, transpired back into the air. They will become part of plants, maybe part of animals that eat those plants, eventually returning to the atmosphere to begin the cycle anew. The physics that govern the droplet's fall, surface tension, aerodynamic pressure, terminal velocity, impact dynamics, all of these were essential to its journey. but they were also essential to the larger cycle. The droplet size determined how much water it carried. Its speed determined how it impacted the ground. Its shape influenced how it spread upon landing. Every aspect of its physics affected its role in the ecosystem. You stand in the rain, letting droplets land on your skin, and you feel the connection to this larger cycle. The water on your face was once in the clouds, once in the ground, once in the oceans. It has made this journey countless times before and will make it countless times again. You are, for this moment, a part of its journey. The rain begins to lighten, the storm passing. The intervals between impacts grow longer, the sound softening. The clouds thin and patches of blue appear. The restorative descent is almost complete. You look at the ground around you and see the evidence of what has happened. The soil is dark with moisture, its color deepened by the water it has absorbed. Tiny puddles have formed in depressions, their surfaces disturbed by the last few droplets. Droplets cling to blades of grass, each one a tiny sphere, a reminder of the shape that your droplet once achieved. These droplets on the grass are not falling, they are resting. They have reached their own destinations, at least for now. They sit on the blades, held by surface tension, their shapes nearly spherical because they are not moving, not being deformed by air pressure. They are at peace, these droplets, their long journeys ended. You reach out and touch one, your finger breaking the surface tension that holds it to the grass. The droplet transfers to your skin, becoming a thin film of water that quickly evaporates, returning to the air. The cycle continues. The sun breaks through the clouds, its light catching the millions of droplets that still cling to every surface. The world sparkles, transformed by the rain. Each droplet acts as a tiny lens, bending the light, creating a display of brilliance that rivals any sunset. You think about the droplet you followed, the one whose journey you have witnessed from cloud to ground. It is gone now, its water absorbed into the soil, but its legacy continues. Somewhere beneath your feet, its molecules are seeping deeper, finding their way into the complex matrix of the earth. They will emerge again in time in some new form. The physics of the raindrop is the physics of connection. It connects the clouds to the ground, the atmosphere to the soil, the sky to the earth. It connects the microscopic world of molecules and surface tension to the macroscopic world of weather and climate. It connects the present moment to cycles that have operated for billions of years. You stand there in the aftermath of the rain and you feel that connection. You are part of the same cycle, made of the same water, subject to the same physics. The water in your body was once in the clouds, once in the ground, once in the oceans. It has made this journey countless times and will make it countless times again. The restorative descent is complete. The rain has fallen, the ground has received it, the cycle continues. The droplet's journey is over, but its story goes on. You turn away from the wet landscape, carrying with you the memory of the droplet's fall. You have seen the birth of tension, the microscopic struggle, the shimmering spheres, the flattened demand, and finally the restorative descent. You have witnessed the silent physics of raindrops, the hidden world of falling water. The sun warms your face, and you feel the first droplets of evaporation beginning their own journeys upward. The cycle never ends. The physics never stops. The rain will come again.